Let's say good morning to everybody. Welcome. So actually we're finishing off chapter 2 today. I've sort of covered, I think, pretty much the chapter 2 material. So I was just going to do a bunch of examples, kind of talk about stuff, maybe shoot a rocket at you or something at some point. Kind of do that in maybe 25 minutes. This week is the first real practical. So last week there was just, you sort of found your room, that was the main thing, and did that diagnostic survey, which I thank you so much for your participation in that. Your answers mean a great deal to me, and I'm using that in my research, and I'll also be using it a bit to set up, probably scramble the pods a little later. But you are working in pods. You probably have a pod number already listed on your items under your grade book. They're numbered. Every table in the room has a number 1 through 9. And you will be working in a small group with 2 or 3 fellow students to conduct experiments, analyze, and interpret results. So the idea is you get your TAs will hand you out a little notebook, and you get that for free. We give you a new notebook every week, actually. And the idea with a lab notebook is you write down your methods, your assumptions, your uncertainties, and your thoughts in sort of journal format. So this is what I'm doing, and you number it, page 1, and then you turn page 2. This is what I'm doing, and so it's not organized by subject or anything, or introduction or whatever. It's just this is what we're attempting. You can number your activities, for example, and refer back to the write-up, but try to write down what you're doing. And then, at the end, your pod shares the mark. So this is one of the reasons we're going to be scrambling teams once in a while, is that try to make things fair. So another way, I find that sometimes people fall into certain roles, and what we want to do is to try to sort of formalize that whole situation by assigning roles and having those roles change each week. For example, someone's usually the manager, someone's usually the sort of lead experimentalist, like the tinkerer or something like that. Then there's the lead theorist, maybe someone who's doing the calculations, and maybe archivist. And so what we want is for you to kind of make a decision. Let's be one of these roles each time. Your TAs will write down sort of the notes of who's who. And then next week, try to switch those roles up. So the manager's responsibility is trying to kind of keep everyone on track, make sure that everyone's included and you're all working together. Make sure that you maybe keep an eye on the time to make sure that you're going to get through the activities in the 2 hours you have. The lead experimentalist, sort of maybe, if something breaks, you're the one to maybe go and get a new one or something, trying to make things work. You may be actually delegating certain tasks to other people. Okay, you hold the cart while I, pull the spring back or something. Or you should also be in charge of describing what the methods were. So this is what we did, and that's going to be an important part of your mark. Lead theorist, sort of checking calculations, connecting things back to the concepts that we have. Like you're going to be drawing motion diagrams and things. So we've done a lot of motion diagrams in class and in chapter 2. So that's sort of the theorist's job. And then the archivist, this is sort of an optional role, but somebody might be the one who's mostly in charge of the notebook and writing things down. And that role should definitely be shared around. You may only, by optional, some pods only have 3 students in them, and that's okay too, in which case you just have those top 3 roles, and you would all sort of share archiving duties. Okay, so I hope that goes well. So I still have my office hours. I'm actually in 125B today from 2 to 3. Then after that, there's something called Vic Peer Tutors. So these are 2 students who took this course not so long ago, did very, very well, interviewed, and they're from Vic College. They get paid to come on over here and try to help you guys out with whatever. And I was part of the whole interview process, and they're also helping out with Physics 151, but they will be there in that same room, and they also have an online Zoom link. And I think to get the Zoom link, you have to email Vic Physics Tutors, and you'll get the presume like on Thursdays 5 to 7. Okay. Those are the announcements. You know, a whole bunch of people have been talking to me about this one. So let me see if I can show you a way of doing this. I don't know if this looks familiar to you. You hike 2/3 of the way to the top of a hill at some speed, let's call it V1, and run the final third of the way at a speed V2. What was your average speed? So this was a problem, it's more numerical, that was part of your online homeworks. But the trick here is that, I'll just put it in the represent mathematically, the definition of average speed, V average, is that it's always the total distance divided by the total time. And so, but you're not really given the total distance or the total time. You've been told that you hike 2/3 of the way to the top of the hill. So I think the of the way implies that it's the distance, not time. It's not that you spend 2/3 of your time hiking up at this speed and then 2/3 of the final third at changing your speed. I think they mean distance, but let's just maybe assume that. So if we sketch it, here's the hill, here's you. You're starting off with V1, and you go this distance, D1, which is equal to 2/3 of the D, the total distance. And then you change your speed. You start running, I guess, for this D2 is D over 3, a third. And D1 plus D2 is equal to the total distance. So this is where you go to V2. You speed up. So we need the total time. T1 is the time for the first D2 over 3 distance, and T2 is the time for the last D over 3. I'm just trying to sort out my thoughts in the sort of the simplifying diagram. So I've sketched the situation. Now I'm trying to kind of organize things. I know that I have this definition. Let's just put it in a box, because that's what we're being asked for. T, the total time, is going to be T1 plus T2, I mean. And V1 is that for that little segment, 2D over 3 divided by T1. So we can solve that out for T1 is 2 times D divided by 3 V1. And V2, by its definition, is the distance D over 3 divided by T2. So T2 equals D over 3V2. So if I'm going to find average velocity, total distance divided by total time, T1 plus T2, it's equal to D divided by, and I'm going to plug in these values for T1 and T2. And they all have D's in them nicely, so the D's will all cancel. 2D over 3V1 plus D over 3V2. So maybe I will just multiply top and bottom by like 3 over D or something. If you multiply the top and bottom by the same thing, then it stays the same. So I get that V average is equal to 3 divided by 2 over V1 plus 1 over V2. And again, let's multiply the top and bottom by the same thing. I'm going to multiply the top by v1 times v2, and the bottom by v1 times v2. Because I don't like fractions within fractions. It looks kind of messy. So I'll multiply. I want to get rid of these fractions on the bottom, and just sort of simplifying this out, I get v average is equal to 3 v1 times v2 divided by 2v2 plus v1. So it looks a little complicated, but I'm taking a definition, which is the average velocity is always the total distance divided by the total time. And you were given certain ratios, but you weren't given the total time, so I tried to solve for that. Okay. Next thing is, I wanted to talk a little bit more. I kind of left you guys hanging at the end of last class with the basketball and the tennis ball. Remember I dropped them? I'll do it one more time. The idea being that they fall at the same rate, which is crazy. I don't know if you believe it or not. I told you that the force of gravity on the basketball is about 10 times more than the force of gravity on a tennis ball. But if you watch them fall, they tend to fall at the same rate. So the question is, why do they do that? Well, I can show you. Whoops, we can do that in a minute. Let's do that. Let's do this first, and we'll come back to that. So this is our observation. We know that if we were to put it on a scale or something like that, the basketball weighs more. So the force, maybe of the Earth, the gravity force pulling down in the basketball is quite a lot more than the force, the E stands for Earth there, of gravity on the tennis ball. However, their accelerations are the same. So why is that? Well, how do you find acceleration? Well, you actually use Newton's second law. So this is looking a little bit ahead. This is a chapter 3 idea. Newton's second law, which is that acceleration is equal to the net force divided by the mass. And so what is the net force? In this case, it's the gravity force. So in free fall, the only force on the object, on the ball, is gravity. That's the definition of free fall, is that you've removed all other forces because you just let it go. When you let something go and the only force is gravity, that's called free fall. And I always think of myself, if I'm in an elevator and someone cuts the cord, then and I start floating around, I'm in free fall. The only force on me is gravity, and the force from the floor goes away. And there's an equation for gravity, F grav or something like that, is equal to m times g, where g is equal to 9.8 newtons per kilogram or something like that. So this is going to be the net force. F net equals that. So what we do is we just take this and we plug it into that. So A is equal to F grav divided by m. So it's equal to mg divided by m. And then the m's cancel. And so you get that the acceleration is equal to g. And the units work out to be 9.8 meters per second squared. So nicely. Newtons per kilogram and meters per second squared turn out to be the same thing. So that's the whole secret. The m's cancel. And another way of putting that is that, okay, if I want to accelerate something, if I just push it with some equal force, well, the tennis ball is going to accelerate way more. You have to divide by that inertial mass, which is preventing something from accelerating. So if they had the same force on them, the tennis ball would go much faster, would accelerate much with a higher acceleration. But they don't have the same force. Gravity pulls heavier mass objects, luckily, with more force so that it exactly compensates. You've got an m on the top, that's the force, and you've got m on the bottom, that's the inertia, and they cancel, and then everything falls at the same rate. Sort of an amazing coincidence. Okay, let's go back. This was the one we skipped. Let's try a learning catalytics question. Now, what we're doing here is thinking about a motion diagram. Now, I have drawn the x-axis. So I have defined positive x to be towards the right in this. So that's important. So if Vx is positive, it means it's traveling towards the right. If Vx is negative, it means it's traveling towards the left. And if Vx is 0, it means it's stopped. So I will give you a minute to think about this one and click in, and then I'll discuss what my answer was. Okay, this is velocity versus time graphs. I find these to be super, super useful. So let's pick one. Going once, going twice. We'll see what people preferred here. I'm going to put a stop deliver. Laptop 2. And so 70% of you voted for D. There was sort of B and A were also like more or fairly popular choices. Let me just see what I think. Let's take a look here. So what I thought was that, so first of all, I think V is negative. It starts here. This is like the start. And at t equals 0, I think. And then what happens is that Vx is negative. And then I guess Vx is even more negative. Then Vx is even more negative. I don't know if that's how you reason through it. Anyway, you guys killed it. Well done. Okay. We did this already. Oh yeah. This is my little chapter 2 aid sheet. These are the 5 equations I keep going to. So this is the one for zero acceleration. It's just sort of the definition of speed. Speed is, another way of putting it is speed is x minus x0 divided by t, something like that. But anyway, and then these are the equations of constant acceleration where a is not equal to 0, including one that doesn't have a, but you know that it's constant. So I might come back to this aid sheet once or twice when I'm actually trying to solve this. But I think there was this question. Do you want to do it? Do you have time? We got all kinds of time. Some people in a hotel are dropping water balloons from their open window onto the ground below. The balloons take 0.15 seconds to pass your 1.6 meter tall window. Where should security look for the raucous hotel guests? This is an end of chapter problem and something that's fair game sort of on a term test. And it's chapter 2. Okay, so it takes a little while for me to just figure out what the heck is going on here, but let's draw the window. And what I think is that the guys dropped the balloons far above your window. So they're not released from rest at the top of your window. They're released from rest somewhere even higher. So that by the time they get to your window, like there, they're already going some speed, V1 I'll call it. And then it's accelerating because it's in free fall. You go to V2 by the time you get down there. It's faster. And I would say like T2 is equal to 0.15 seconds. It's the time to go from T1 to T2. So I could say T1 is 0 seconds. So during 0.15 seconds, and you pass this distance, 1.6 meters, then you've changed your velocity somewhat. And this is like the time, T2, to travel the height of your window. Okay. And what you're asked to do is to find, I think, it says, where should security look for the raucous hotel guests? Let's just reword that. Find how far above at the top of my window did it get released from rest? Was the balloon, maybe they threw it, but maybe they just dropped it from rest. I think you have to assume that. From rest. Okay, so that's sort of my assumption. I'll say assume that the initial drop was from rest. And then I'm going to divide the motion into segments. I know you guys don't like it when I do that, but there's the time before T1, I guess T0 or something like that, some negative time. It was dropped from rest, and then as it passes the window into 2 segments. There's other ways of doing this, but this is, I think, the easiest. Before the balloon gets to the top of my window. So V0 is 0. That's the initial for segment 1. Initial. And then V1 is equal to its final. And what I need here, the thing that I care about is Y1 is the distance traveled. That's really important because I think that's the actual answer, is how high above the top of my window were the raucous hotel guest. And in this segment, I think I don't care about the time it took. About the time it took. I guess I'll call it T1 or something like that. But anyway, for segment 2, V1 is equal to the initial, which is the final of segment 1. So we're going to care about that. And T2 is equal to 0.15 seconds. And Y2 is equal to 1.6 meters. And I think in this case, I don't care about the final speed. V2, final speed. Okay, so, yeah. Whoop. Yeah, this was just to remind me to shoot rockets into the crowd. So we're We're going to continue in this. So what's my next step going to be is that I'm going to try to look for equations from my handy-dandy aid sheet. And the one that for segment 1, I'll use one in which I don't care about time. And for segment 2, I'll use one in which I don't care about final speed. So where's Pius? He's left me. Maybe I should wait for him. You guys ready? But first I'm going to shoot a rocket at you. But they're hopefully not. They're like foam rubber. So hopefully it's not going to really hurt anybody's laptop. But we're going to think about projectile motion. And so if you're looking at it from the side, you can try to follow sort of the parabolic arc of this thing as it goes. Ready? Oh. There must be a launch button. There we go. I didn't hit anybody. Okay, and then we'll do one more. So I'm going to shoot it at that other exit. I just have 2. No one died in the first one, so let's see. Oop. Ooh. Okay, nice. You almost caught it there. All right. So, what are we going to do? Let's go to segment 1. And we're going to use, which is the one that we don't care about time? 2.7. Equation 2.7 doesn't have t in it, and we didn't care about t for segment 1. So let's use equation 2.7. I will need those rockets back at some point. Like I say, my guy has abandoned me here, but it's okay. And then I'm going to solve for V1, and that's going to be, oh, thank you. That's going to be the final velocity for segment 1 and the initial velocity for segment 2. So it looks like this, 2 times a times y1. And so instead of x's, I'm going to use y's. I hope that's okay, because it's vertical motion. v1 squared minus v0 squared. Now, v0 in this case is equal to 0. I'm going to set y0 is equal to 0 as well. And a is equal to g, which is 9.8 meters per second squared. Oh, Pius, you totally missed it, man. I almost hit somebody's laptop. I shot the... So I got one back. I don't know where it came from, and there may be one over there. You saw me in the middle of an example, and you're like, hey, he's not going to shoot the crowd right now. Okay. You'd think. Okay, so I can plug in a lot of these things. Let me just cross out what are the zeros here. This one is 0, and V0 is 0. So it looks a little simpler. 2 times g times y1 is equal to v1 squared. So we're going to get a square root. v1 is equal to the square root of 2 times g times y1. Okay, so that's segment 1. Segment 2, the thing we didn't care about is, I think, the final speed, the water balloon as it passes the bottom of your window. So, which is the one, yeah, so let's use equation 2.6, this 1/2 at squared thingy. So let's use equation 2.6. And we're going to solve for V1, I think. Solve for V1 because we know that from the previous. So I get that y2 is equal to V1 times T2. That's your initial speed times the total time, plus 1/2, I'm going to put g here, and T2 squared. So if I solve that for V1, which is sort of the initial speed here, y2, it's sort of weird. I'm solving for initial speed here, and that's going to be, I'm going to make that equal to the final speed from the previous segment, g T2 squared divided by T2. So what I'm going to do here is set V1 equals V1, and I'm going to use this equation for V1 and plug it into the left-hand side, and I'm going to use this equation for V1 and plug it into the right-hand side, if that makes sense. So I get that square root of 2 times g times y1, square root, is equal to y2 minus 1/2 g T2 squared over T2. And I think that's all the tricky stuff. And then it's some algebra after that. So I'm going to square both sides. 2gy1 equals all this stuff squared over T2. Square that whole thingy. Solve for y1, which is what you're trying to tell the security guards. 2g, again, I have to write all this stuff out. Divided by T2 all squared. Somewhere here it should actually say solve and evaluate. Remember that last step? We're on step 4 now. Y1 is equal to 1 over 2 times 9.8 times 1.6 minus a half of 9.8 times 0.15. Should be squared there somewhere. Squared, squared. Don't forget to square the whole thing. Divided by 0.15. So I plugged the whole thing into my calculator and I got 5.03. And I don't really know what to do about the units, but I think it's distance, so it must have been meters, right? So basically, security should look 5 meters up, assuming that the raucous guests are releasing the balloons from rest. Maybe that's not the best assumption, but top of my window. It'd be really hilarious if you did all this math and you told the security guards, and you're like assuming for us, but actually the guys were throwing it, and they're like way higher. Anyway, okay. All right. Should we do, you guys okay with that? We've got some time. I got another good example, and 3 more learning catalytics, and then we're done for the day. Yes? Yeah. This one? Yeah. No, that's a really good point. Somewhere in there, I kind of set initial, way back at the very beginning, I only measured the distance from this t equals 0 start, meaning that y0 is some negative number, I think, and it starts there. So I don't know, I was a little sloppy there. But I didn't care about that initial distance. Y1 becomes the distance before that. Yeah, there's definitely, I completely understand what you're saying. From here, this is going to be the distance. Maybe another way of putting it is this is y2 minus y1 or something, and you're solving for this delta y or something. It's a really, really good question, I think. It's just it was maybe a little bit sloppy of notation. Okay, let's deliver one more of these questions. In this one, what you're doing is you're given remember in the last one, you were given, I guess, distance versus time, or you're given a motion diagram and you're asked which velocity graph. Now you're given, I want you to think backwards. This is the velocity versus time graph. Which of the position graphs matches the velocity versus time graph? Just maybe about 30 seconds and we'll discuss this. Try to click in and answer. All right. How are we doing here? Let's look at what class voted. Laptop 2, send to all. So I can sort of see 87% are voting for D, sort of a smattering with some other ones. So what I think of here is that the velocity versus time graph is the slope of the position versus time graph. And so this has a slope 0, right? Slope 0, not moving. So that can't be right, I don't think. This is good. This has a positive slope. But then this has like a, I don't know, some sort of very negative slope. I don't know what that is. It's negative infinity or something like that. It goes straight down, it looks like. And also, it seems a little weird that something can just teleport from one place to another. So this is, I think, maybe not possible. It's good, actually. I think that, in a way, B is correct, except for the not possible teleportation part. And this one is not, right? This is the 0, and then it starts moving backwards, and here we go. So here, it's exactly like B, except without the teleportation. It goes for a while at some speed, and then it stops. Maybe it hits the back of the net, the hockey puck stops, and is at that same position where it stopped moving. It doesn't just jump, okay? Okay. So I got one more example and two more little conceptual questions for you. Here is the velocity graph of an object that is at the origin, x equals 0 meters, at t equals 0 seconds. At t equals 4 seconds, the object's position is blank. Maybe it's a multiple choice question or something. And then you're given a list of things. So you have to work this out. Sometimes this happens a lot on term test questions, is that you're given a question and there's 4 answers or 5 answers or something, A, B, C, D, E. But you can't just look at it and figure it out. You have to kind of, again, work through this whole process, maybe on some scratch paper or something, to try to get it. So, okay. At t equals 0, x0 equals 0. And the Vx versus t graph is given. Okay? So I'm sort of organizing my thought here. And then what I'm going to say is I remember from the notes somewhere that the area under the Vx versus t graph gives the change in position. So that's going to be your whole key here. Delta x is equal to, I guess, x final minus x0. So what we're going to say is that delta x is equal to some area. So what's the area? It's just going to be the area of that thing, area of that shape. So what we can do now is divide the shape into a square and a triangle. Call it A1 and A2 equals A1 plus A2. A1 is a square. So what's the area of a square? It's length times width or something like that. And A2 is triangle. And area of a triangle is 1/2 base times height. Something like that. Sorry about the messiness. Anyway, this is a geometry problem. So A1 is going to be, let's just write it down, LW plus 1/2 base times height. It's going to be the length here is 2 It's sort of weird that we're doing seconds and then meters per second, but don't worry too much about the units. Maybe they'll just all work out. I guess actually, if the units of the one sides are seconds and the units of the other are meters per second, when you multiply those, I think the seconds will cancel and you get meters, which is what delta x is in. So I think we're actually okay. So let's just say 2 times 4 plus 1/2 of 2 times 4. So if this is base, right, and this is height, and this is length, and this is width. Apologize for using all the different letters, but you get me? I've got delta x is equal to 8 meters plus 4 meters is 12 meters. And x0 equals 0, so x is 12 meters, the final position. Okay. It's kind of like integrating, but you're finding area under the curve. And by under, I mean that green line shows the velocity. You find the area between that and the t-axis where velocity is 0. And if your shape is underneath that, then you can find the area above it to the t-axis, and you get a negative area in that case. Okay, let's do another question here. This one is an interesting one. This is about a test of a car's acceleration. So sometimes they publish how fast a car can accelerate by giving you the time that it takes to go from 0 to some final speed. It's usually 100 kilometers per hour. So this is 2 different tests. We're testing my old Toyota Camry versus a Porsche 918 Spyder. And so they both start from rest. The driver presses the pedal to the metal and accelerates as fast as they can up until they get to 100 kilometers per hour. And that's the test. The question here is, during the test, which car drives the longer distance? A, the Camry, B, the Porsche, or C, they both travel the same distance? The test ends when they get to 100 kilometers per hour, correct. And this is asking about the distance. Yeah, that's another good way. I've heard 2 good ways of solving this. Let's see what people are answering. Look at this. You guys are too good for me here. I'm gonna give you 5-second countdown. 4, 3, 2, 1, and stop. You guys, I'm impressed. This was a hard one. And I'm seeing A, the Toyota, 79%. And so I saw 2 ways of, or I talked to students who had 2 different ways of reasoning. One was actually using that area of a triangle thing we just did. These are both triangles, and they both go from 0 up to 100 kilometers per hour. And then so the height of the triangle is 100 kilometers per hour. The width, or whatever, the base of the triangle, in each case, is the time it took. So the triangle for the Camry has a base which is 6.5 seconds, and the whatever it is, the Porsche has a shorter time, so it has a smaller area. So that's one way of looking at it. And then another way of looking at it, which I also like, even easier, I think, is to say, remember that whole thing I told you about average velocity? If the acceleration is constant, which, by the way, is the assumption, maybe I should write that down. Let's assume, if you don't do this, you can't even solve this, that acceleration is constant. Even though it's not. But if you assume that, then the average velocity is the initial plus the final divided by 2. And so in this case, it's 50 kilometers an hour for both of them. And then the distance traveled is the average velocity times the time. They both travel with an average speed of 50 kilometers per hour, even though it's a Porsche. Isn't that interesting? It just gets there faster. Okay. And then one more. And I think we're pretty good. You guys, this is another tricky one, but we'll see how you guys do with it. Deliver. Should see it on your phones. It says, Heather and Jerry are standing on a bridge 50 meters above a river. If you can get a picture it. Heather throws the rock straight down with a speed of 20 meters per second. So it's not releasing from rest, it's throwing it. Jerry, at the exact same instant of time, throws a rock straight up with the same speed. Which rock has the faster speed as it hits the water? Neglect air resistance. I think I'm going to have to draw this because it's... So go ahead and discuss, and I'll try to draw it. If you guys like my diagram. You always put numbers. Okay, let's just finish this one up. Oh, this one's even more controversial. So click in and answer, please, and then I'll tell you what I think. Going once, going twice, and laptop 2. So 52% voted for C. Okay, and I think that's what I was going for here is that, so a couple of things. First of all, you neglect air resistance. Second of all, you, when it says as it hits the water, what I always mean there is like just before it hits the water. So it's been in free fall the entire time, and just before it hits the water, which one hits the water with a greater speed? So clearly, Heather's rocket just goes straight down, hits the water with some speed. Jerry's rock, what I would argue is that it goes up, stops, then comes back down, and when it passes Jerry on the way down, it's actually going 20. That's the kind of what goes up must go down philosophy. Is that if you throw this thing up, then when it comes back down, it's going the same speed, but in that it left my hands in, as it passes, it's going that same speed going down. It's just reversing its velocity. And then after that, they're the same path. Same distance, same initial velocity, so this one has to end with the same velocity. It's later, but it's the same final speed. So let's see. And I'd like you to start reading chapter 3, and I'll talk about that on Wednesday. Bye now.